Hit the button. Making video production, DraftScience and such. Mostly draft physics. Anyway, science, big category. Philosophy, physics, subcategories. Subcategories of physics, chemistry, biology, all the other bullshit. Anyway, so comments. There's probably be enough in the one comment, frankly, to make a whole video. It's nice. Perv Action. Not a great name, but whatever. Probably stands for something. Not bad, but who knows. Yeah, anyway. I mean, all the little distractions. There's always, the little bullshit people worry about. But anyway. I know, here I am emphasizing something somebody shouldn't care about, but whatever. Alright, I'll get to the video. Just trying to, get through my humanness first so I can do this robotic, mechanical science thing. And the human's resisting somehow. Somehow my personality is resisting, going into thinking mode. Alright, anyway, what do you imagine the proton force to be generally doing compared to the electron force? Well, there's no distinction between it's doing the same thing. The question is it doing it in some other way? Is there some piece of evidence that indicates that protons are fundamentally different than electrons? And the only thing I would argue at this stage, having not given it an extensive amount of thought, is that I'm sort of arguing there's different ways to create polarization. So the idea could be is that you have a proton and you have an electron, and that's polarization, right? I mean, you got the little negative thing here and the little positive thing here, and you're all done. But the other part to it could just be that this is about distance. So from a perspective, I can change this polarization by just moving this from here, okay, to some other location, and say now that creates the polarization, because now this is a negative atom, because the negative is closer to the eye, you could argue. Or you could say it's a positive atom by making some opposite argument about the shadow. The shadow of the electron on the proton is now much smaller, if it was to have a shadow. Weaker, let's just say. And, you could use that as an argument that this force gets to more places because this one's blocking less of it. So you could argue that depending on how much this eye is catching, obviously this eye could be much bigger. You have a really big eye. Then more of this green stuff is getting to the eye, the further away this electron goes, and that's a form of polarization. So you could argue that when the electron is in this position, it's more electron, because the electron is now blocking more of this stuff. Okay, it's getting blocked by the electron, and a lot less of it is getting blocked here. Just a tiny percentage of the overall energy. And you could say that's a form of polarization. So it all depends on sort of how you think about the structure. So I'm certainly arguing that there's an intuitive or a simplicity in just saying, yeah, they're simple, they're opposites. And I'd suppose the fact that magnets are so consistent in terms of having the same amount of south end as they have north end, and maybe you could use some other arguments to say, well, it sort of indicates, and certainly conventional physics has found a kind of a one-to-one relationship between the number of protons and the number of electrons in most atomic structure. So I guess I would just argue that the basic idea, that you have these neutrons, and that's holding protons together, is I would say logically valid, and the idea that the nucleus is just a combination of these objects, well, that was the wrong way to draw it, but anyway, you get the idea. That's a nucleus, and that the electron is something floating above. Now, I've committed to no argument about how far away it's floating. but clearly what they're saying is that it's orbiting, and I would argue there's a little bit of trouble with that. I mean, part of me says, okay, cool. But the other part of me says is we know that momentum is going to get consumed because this external force is coming in, and it will see this extra motion in a direction in terms of it sees motion. I mean, the force sees motion in a sense, and it is more likely to make exchanges with the motion, and therefore the motion is going to be equalized to the force. So it's always going to try to take your motion away. So drag is a real issue. And if drag's a real issue, you can't do this Earth orbiting the sun thing forever kind of argument, because these aren't material wrenches. They're protons and electrons resist motion more substantially, say, than heavy matter. All right. So maybe that's enough to add. I mean, like I said, I have no solid description beyond the fact that I'm saying motion is unlikely. It makes more sense in connecting atoms to understand that they are actually sharing an electron. So when two atoms are connected to each other, they're literally connected. I mean, there's an electron in a location, and the two atoms are sharing that electron. It's not doing any figure eight crap. It's not floating around, because as I've sort of pointed out, it would spend more time not connecting the atoms, okay, where the two magnets would be broken. Their magnetic hold on each other would be broken more often than it would be connected, and therefore there's not much likelihood you're going to create strong material bonds. I mean, stuff doesn't fly apart easily, and it would if all of this was this mushy figure eight crap. That's a very mushy, in my opinion, way to connect two things, is, you know, to have it move around. If they're sharing food, the food isn't, you know, sliding over to my side and then slides over to your side and slides, you know, we're chewing on the same thing at the same time, so to speak. So anyway, analogies. I mean, I don't pick them ahead of time. It's just whatever flows out of my, you know, personality. On one hand, its counterpart is less exposed. So that's sort of the opposite, right? On the one hand, its counterpart is less exposed. The electron is more exposed than the proton. On the other, there is much more empty space in an atom. So now that's sort of an interesting question. How much empty space is there really in an atom, and what evidence do we have? And so I guess the primary piece of evidence, I don't know if they have any other kind of evidence, but the primary evidence is, you know, they just take some thin piece of metal like gold leaf or something, some piece of something, and they just shoot a bunch of nucleuses at it. So they're heavy things, and they shoot them, and they say, how often do we hit a nucleus? But see, the nucleus ain't going to be bothered by the electrons. So if it hits an electron, it ain't going to matter, because it's, you know, it's just a steamroller hitting a butterfly. I mean, that just ain't going to matter. I mean, that seems like an exaggeration, just because the nucleus isn't that heavy. But anyway, regardless, the electrons aren't going to do much to its motion. And what they're saying is, how often does this thing catastrophically hit something, in the sense where it bounces back? Now, bouncing back would require kind of perfect circumstances, in the sense that what you're hitting has to be in no pressure, in a sense. So, I mean, it has to be pressurized. That is, there has to be something to do the pushing back, right? There has to be some kind of spring. So that means there has to be enough density of atoms for you to get a pushback. So, you know, first off, they're using a material thin enough to get stuff to go through it. So that's part of the equation, right? Is not so much how you have to make some kind of assumption about how many atoms you're trying to get through, okay, to have some sort of action. So you have to, the spring action sort of requires there to be a nucleus and a nucleus and a nucleus and a nucleus, and you're pushing into their pressure and they just want to re-expand, and they push back to push the nuclei back out. So getting the back out reaction isn't so much hitting something, it's hitting something that's sprung. So you're not going to get any back unless you hit a nucleus that has a spring. All right, you can't really see the spring. I moved over for the whole purpose of showing more of the board. So, unless you have one that's loaded, you're not going to get it back. All right, and what you're going to get, more likely is something comes out this way or something comes out this way, because it bounces off the force it's coming towards, right? So these nucleuses, generally speaking, don't like each other. They're positively biased, substantially. Mostly proton in the sense, right? A smaller number of electrons. You could argue, if you count the neutrons, it means there's half as many electrons as there are protons in the nucleus. And I'm just going by the fact that when they degrade a neutron, when they let it sit alone, it does fall apart basically into a proton and electron. But anyway, these are all things that are deduced out of these kinds of experiments. So the point is their analysis of the experiment, if it doesn't understand the spring thing, well, then it thinks the time it bounces back is because every time it hits a nucleus, it bounces back straight. Well, obviously it'd have to hit directly first. If it hits at an angle, because these are forces, it's like two electrons hitting each other. The electrons never hit each other. They sense each other's force and they deflect off each other. Okay, so they never hit each other. So you get these. So anyway, the point is they get a certain number of these helium nucleuses fly out at some crooked direction. Some go straight through, and then some bounce straight back, and some bounce back crooked. So they don't get too many crooked ones. I'm not sure. But anyway, the point is they're just counting how many of these they get back, and they're making an approximation about the size, how small the nucleus is, based on how often one flies back. And I'm just saying how often one flies back is a little complicated. So their description of this empty space is just based on them calculating how hard it is to hit a nucleus, but I don't think their experiment can tell them how hard it is to hit a nucleus. It's telling them how hard it is to hit a nucleus that has a couple of atoms behind it. All right. I'm just saying the evidence is mushy regarding how much empty space there is in an atom. And I would argue that their theory kind of, on its face, sounds a little iffy. We know that, the atoms are really small, right? An apple is to the earth what an atom is to an apple. It's an insane number of atoms. So, in substances. So, it's this problem of figuring out, if you have this insane number of them, it's, inevitable you're going to hit something just because there's almost nothing thin, right? Nothing a couple of atoms thin or something. So it's a little hard experiment to do. Anyway, where you're going to glean this information about how much empty space, how likely you are not to hit something. It's a little tricky. What else do I want to say on that? I just would say on the face of it, it seems like electrons are pretty easy to hit. Two-slit experiment, for example. I'd say they don't have to be that dense, so I think they got to be a little bigger than they're thinking. The balloons have a little more air in them. But anyway, I don't know if it's a very important question to answer, but it does have to do with your whole perception of what an atom is, in terms of this idea of peanut in the middle of the football field and the electron is out in the stand somewhere. That's sort of I think an exaggeration of the reality. Wait, do you even subscribe to that? Yeah, so I don't subscribe to anything because I'm just saying there's really not enough evidence to draw these kind of conclusions, I don't think. But whatever, it doesn't really matter, I don't think, to understanding, except there has to be some kind of distance between them because there's a lot of energy between them, right? I mean, the E equals mc squared thing is telling you there's got to be at least room in the atom for a bunch of energy to be in there. That is, of course, if it's an explosion, rather than an implosion. So I mean, I could theoretically still argue that you can implode. It's the absence of pressure that's really being exposed when you break an atom. So you could theoretically, I think, still argue that when atoms implode, they cause a lot of aggravation to the other atoms and they sort of explode. But that's another train of thought I haven't driven all the way down the tracks, so I don't know if there's much point in me opining. Could we test for the proton force existence? Right, so that's the sort of an interesting one, is that we have the phenomenon of electrons where everything we know about them essentially is gleaned based on electromagnetic radiation spectrum, light, photons. And is there some way that we could see the other force? Like we don't see gravity. We can't test for it any other way than to watch whole pieces of matter fall. But with electrons, we can do this little trick where the electron is, capable, in my opinion. The simple argument is we hit the electron with a pattern of energy, and the pattern of energy is such that the electron, because it's in tension with the rest of the atomic universe, the electron moves in a kind of a weird position, changes its position, and then swings back. And in swinging back, it essentially gives back what it absorbed. Okay, and by this sort of drag mechanism that you can't really move unless you change what's in your boat. So if you're going to go one way because a bunch of things jumped in your boat, right? These guys jumped in the boat. Then to go some other way, you're going to have to give back that. So if you're going to get back to the same position, you're going to have to essentially give back everything you took in. And the density of the field essentially dictates the frequency. So I could sort of argue that the pressure of the field is essentially illustrated by something like the infrared spectrum, right? Infrared light is the most likely thing that's going to pop out. And to get the same frequency back, this circumstance has to be a little bit special, let's say, like inside of a piece of glass that's transparent, or some other thing that gives you back the same frequency you put in. See, I mean, with an opaque object, you're basically, you're putting in a frequency that is, whatever, X. And no matter what you do, no matter what frequency you put in, you get a hell of a lot of this Y stuff out, this infrared. You get so you put in any number, 300, 700, 900, and you always get back whatever, 752, every time. It comes back the same way, or 900, or whatever we want to use for infrared. And that's, we get back the same crap. And so that's just because the circumstance in here, the drag factor, in terms of the exchanges at the rate that the thing attempts to get back, the rate it can get back is the same rate as the exchange rate that has to happen. So it can't exchange any faster than the field that it's in will allow. And so it always has to give back the same. All it can do is convert nickels. So it converts nickels because that's, so you can make it go. You can throw quarters in, but you're only going to get nickels back. That's not the best analogy. Okay, so anyway, that's how we see electrons. That's how we understand their force, is because we can do this frequency thing, change the position of the electron shoots a new photon. The new photon is just giving back what came in as the electron moves back to its original position. All right, so the argument would be that in the nucleus, where the protons are, that's dense, and you just can't do anything with it, right? I mean, so the nucleus has got the protons very close, and so, you know, you're saying, so they're in high tension, you know, kind of a rigid tension, really close, and there's nothing we can hit them with, you know, in terms of a pattern that causes them to move to some new position and then move back and give back that pattern. So we don't really have a way of sending energy in. We can't do the tipping thing. The electrons, you can tip them out of place and force them to move back. You can't really do it to the proton. You could probably just push it this way, or a little bit of movement, and it's just not enough movement. You can't create enough frequency that we can make any device to detect that frequency. But the only way to detect it is to shoot it into an atom with a nucleus and have it repeat the same effect, you know. So I mean, you know, we can't do it. The whole magnetism, electricity thing all works because it's all working on electrons. All of those spectrums, all of those functions are a function of moving an electron to a new position, and we just can't detect the position changes of protons because the position change is so small by comparison to the position change of the electron. So we just never get enough frequency, you know, enough length of ray, okay, in the proton spectrum, if I can call it that. All right. I think that qualifies as a complete enough answer. How would you go about growing a magnet from the ground up with current technology? You know, it really just, again, you're back to this quiet argument. So first, you have to make it insanely cold. So, you know, if you want to make a perfect magnet, a more perfect. I don't think a magnet can be perfect just because of there's some waste in the basic configuration of the magnet, in the sense of the theory is you're stacking a bunch of these lopsided atoms on top of each other. So if I drew the magnet like that, I could argue that what that really represents is an atom where there's an electron. You know, maybe it all just takes one. Maybe 2 electrons would be better. Maybe that's what makes the difference between something that's magnetic and something that's not, is the number of electrons that are part of the imbalance. But I could argue that that doesn't really represent what that looks like. That just represents that, say, you have the nucleus here and the electron is further away. Not that it's polarized, just that it's further away from the proton. You know, so you could like, say, if you had 2 electrons and one of them was further away than the other, so there was just an imbalance in the atom. Well, that's the same thing as polarization, right? From one side it looks green, and from the other side it looks red. But it really just has to do with the fact that multiplies, so that if I stack these things on top of each other, what I'm getting is a consistent pattern of where the energy comes in. Okay, like, let's see if I can draw this correctly. Well, it's this whole tends to move in a direction thing. So the energy, you know, comes in here and kind of comes out here, or keeps going here, you know, and the green is all pushed this way, and the red ends up being pushed this way. Okay, so, you know, if you're going to say how do you build a perfect atom, well, first you have to build a perfect dipolar atom, and then you just stack the dipolar atoms. But the biggest problem to the formation of magnets is heat. So you know that the heat's going to be your enemy. Any kind of noise that causes these things to shift position and go crookedy, okay? I mean, if you just need a little bit of crookedness to understand, you know, in these magnets, to understand that now you've broken this flow in a direction. You know, you're not going to get the flow of the energy through this broken thing because now you're going to get wrong turns, you know, and the energy is going to be coming out in all kinds of wrong directions. And so you're not going to have that good segregation. And what you want is this ideal segregation. You want to basically have something where the mixed force comes in, and you more perfectly have this effect where, you know, let's just do it from one side of it, you know, just to make it visible. So you have mixed force coming in, right, to the magnet, and the basic effect of the magnet is to segregate. So all the red stuff ends up coming out this end, all the green stuff comes out this end. And so you're just talking about how do I perfect that mechanism. And as a, you know, I'm just saying that there might not be anything perfect about its function. Even the atom that's perfectly dipolar isn't going to be perfect. So you're just talking about anything that's going to appear magnetic if it just creates a little of this effect. So it goes from this being, say this was blue and red, and you can understand that this is purple stuff coming in, and any filtering you'll see, oh, this is a little bit bluer, okay, not completely blue, and this is a little bit, you know, redder. And so any indication of that is something that could be multiplied by the atom and create the effect of magnetism. And obviously how perfectly it can do that, I would say there's probably a huge limitation to how perfectly you're ever going to get an atom to create this filter. It's never going to create a filter that's perfect. All right. It doesn't have enough structure to make a perfect filter. All right. Cost not being an issue. So I guess the actual with current technology. So the argument would be is they're already applying some current technology in the sense that they're already trying super cooled things and they create much better magnets. They call it superconducting, but it's basically this idea that you can, in a super cold substance, you don't have to worry about these magnets constantly moving and jiggling, and so your filter works a lot better. All right, cost not being an issue, but the condition is you have to build, grow in a vacuum from single small parts. Well, obviously the inside the atoms is all a vacuum. I mean, the empty space out there is the same as the empty space down there. So there's always a vacuum around everything. Technically we're in a kind of a vacuum, except a bunch of atoms are hitting us. I mean, what can I say? There's still a vacuum around all those atoms. It's just that the vacuum is dirty. So, you know, it's really just how much dirt is in your atmosphere as you're talking about. So yes, you need a clean atmosphere. Well, we're back to a heat argument or something. Yes. Anyway, cost not being an issue. Okay, so single small. Okay, cost not being an issue, but the condition is you have to build, grow in a vacuum from single small parts and have only the smallest parts. And have to only use smaller parts than the current product. Well, again, I'm saying kind of quite clearly that I think the elemental function of the whole thing of magnetism is the atom. I mean, it is the electron and the proton. They're the elemental charges. I don't think there's something more elemental than them that's charged. So I think that's where the conversation starts. Is you're just stacking electrons and protons. All right. Smaller parts than the current product. No submerging, mixing, or other steps involved. Large quantities. So I don't know what you're asking for here, but yeah, no, I don't have any patents pending on better magnetism. Haven't even given it any much thought. You could argue that this whole neutron thing and neutron stars, it gets sort of interesting because you could, you know, fundamentally neutrons aren't really neutral, right? So I mean they have this kind of lie name. They're like the smallest dipole, And the trick is, if the smallest dipole is spinning, who knows what it is, right? Or if there's a balance between the distances, then who knows what it is, right? So you could argue that stacking the electron on the proton, in some way their proportions are in some configuration, where from either side somehow they look neutral. But I think you really have to start spinning a neutron. I mean, for the neutron to work, it has to spin, and the reason why when you isolate them that falls apart is, I think in free space they have to be spinning. Yeah, well, I mean, the very fact that they form a nucleus kind of indicates they must have a charge, because they must bond with something. So in a sense, the whole notion that they don't have a charge just doesn't work. But the idea would be is that the reason why we can't detect their charge is because we have to hold magnets up at them to see them, and in a way that's defeating the purpose, because we're both shooting purple light at each other. From a distance, it's all purple. So there's no, we just can't get close enough to a neutron to attract it, to detect that we attracted it. Maybe that's just a measurement problem. All right, but anyway, moving on. What is your best guess for the shape of an atom? I think it's electrons and protons fundamentally, and they're either this big or they're this big or this big. But a bunch of repulsive spheres fallen into semi-stable positions around raspberry-shaped center. Well, something like that. But there's a lot of, I think if you really saw the atom, it's going to get kind of interesting, in the sense that the image is going to be a bunch of stuff shooting in directions, a whole bunch of energy. So the electrons are going to be like laser beaming each other with a lot more energy, in the atom. So it's got to be like big hunks of, lots of lasers going off, and then the proton is going to be lasering out this way, and lasering this way, lasering this way. So it's going to be, I guess I should have done that in the opposite color just to get the idea. So there's going to be lots of this kind of crap going on, and those beams are going to be turning on and off, and getting brighter and weaker, and because all this stuff is going to be, in tension. So it's all going to be rocking back and forth and doing some jiggling in those positions. And so all this stuff is going to be, it's going to be a pretty good light show, I guess I would argue. All right, a bunch of, yes, okay. You generally accept a nucleus. Why wouldn't shells make the most sense? Well, again, I haven't really argued any of this stuff, but I guess, when you start thinking about it, so he's kind of arguing that you would have a layer of, say, proton, and then you'd have a layer, of electrons, lumpy bits, and then you'd have some more protons and out here with a neutron or something, and proton, electron, neutron. So you could make some kind of shape where the two are interacting. But then I'd argue that you'd have a much higher likelihood of being able to interact with protons, and you'd end up with a whole electromagnetic spectrum that was proton sensitive. So the very fact that the thing is durable, I guess I'm saying that the more durable object is the one with the heavy nucleus, and if you start spraying the nucleus out, you start making it less durable. So I guess that would be one of the arguments you could make, is that the thing has to be able to survive in a very different pressure environment than what it was formed in. So let's say it was formed inside a sun's that's really high pressure, and that's what it's made to live in. So that's what it was designed. And the fact that you can put it underwater, it's like you make a car, and some cars can go underwater, some cars can't. That kind of argument. It's surprisingly durable. So, you can take it out of its pressure and it still stays together. And those are the 100 elements. You know, is this stuff that will stay together when you take it outside of the sun, outside of its birthplace, outside of the womb. It survives outside of the womb. Okay. Not the orbit kind, more like layers. See, I'm just envisioning it as, we can see this with magnets. Like I said, if you put magnets between a couple panes of glass, you can arrange the magnets and they'll stay in their positions, and you can create all kinds of pressure between the magnets, and it works. So I'm just saying that I think it's just more likely that that's what it's built out of, not layers that would create all kinds of conflict between the different layers, would have lots of conflict with each other. So the idea that all the protons are in the middle and all the electrons are repelling each other, I think makes more sense than trying to make layers of protons and electrons and then somehow have them in all the right positions where they don't repel each other more than they're allowed to. Alright. Layers of geometric balls naturally arranging in pyramids or something. Okay, not the orbit kind, more like the layer of geometric balls naturally arranging in pyramids or something. Yeah, no, I just don't see it happening, just because it's a strong force, this charge thing. How wild is the jiggling vibration of an electron relative to the atom's radius? I don't know. Yeah, good question, maybe. I don't know. That's like way too... It's just that we know that a photon has the capacity to do something that is substantial. So it creates enough momentum in electrons to cause an action that has a reaction and all of that stuff. So, you know, the energy goes in, the energy comes out, you could say, so, but it comes out rather consistently and all that kind of stuff. So the jiggling can't be more than that. It can't be creating more noise than the electron can cause. I mean, than the photons can cause. So it can't be that noisy. But the fact that I'm arguing that the electron has a state where it has an odd number of boat seats. So, I mean, I have really gone over this so many times that you should have gotten this one by now. But the idea is if I had a boat and I only put 3 seats in it, and the only thing that can sit in this boat is a guy going this way, a guy going this way, well, you know that it's always going to be odd, you know, an odd number of seats. I'm always going to have a bias in a direction. So I'm saying that essentially the electron always is going somewhere, and you're just taking something, so, you know, it has to jiggle even when it's not, even when there's no external force hitting it. No new rowers are coming in. It still has a directional bias. You know, it always moves. And so you're just saying once I have it in pressure, then this bias will just keep flipping. You know, it'll just keep flipping from being right-handed to left-handed, right, left, right, left. If I have a even force coming at it, it's just going to flip back and forth, back and forth. So it's like having a penny on its edge, and then you flip a coin over here, decide which way it flips. You know, so there, if I have randomness in these heads and tails, I'll end up with randomness in how this is flipping too. So it won't go anywhere. I won't have 400 million of them in a row or something. It won't go in any direction, because it'll constantly just go, well, if there's a bias of 3 in this direction, I'll just end up eventually having a 4 in the opposite direction. I mean, I'm never going to be able to escape the randomness, the apparent randomness of the field. All right. How wild is the jiggling vibration? Okay, we did that. All right. What was it you suggested the distance between photons and electrons to be responsible for again? What was it you suggested the distance between protons and electrons to be responsible for again? Well, again, I'm just saying you have to hold the force. So the pressure between the electrons have to be close enough where they're pretty strongly attracted to the proton, because what's balancing that attraction is the repulsion between the electrons, right? The repulsion of the electrons is balancing against their wish to go towards the protons. So those two forces have to be in balance. That is, the electron's pressure has to be as strong as the shadow being cast by the electrons and protons relationship. And so you have to do the E equals mc squared thing. You have to somehow create it in that mechanism, this insane amount of energy. Okay. What was it? So, I mean, it has to be space. The force has to, I mean, see, obviously the energy argument ends up being against this ping pong paddle thing, right? I mean, the closer I bring them, I have this infinite thing almost, where you could almost imagine an infinity. So they have to be close enough where they're really multiplying the force. There's lots of vibrations between them. And that's really all we're talking about, is this, that's the pressure, right? So it could just be one ping pong ball. But when ping pong ball between two objects that close, two negatively charged objects, they're in a fundamentally unnatural condition. So the energy really is just about the proximity of the electron. So you could argue that the entire notion isn't that you're storing. So I was sort of saying the wrong thing to say that, oh, they have to store this tremendous amount of energy. They're not storing energy. They're storing it in the form of proximity. So all you really need is one piece of energy. So if I have two things that are repulsive, and the argument is they're perfect mirrors, and I inject one ping pong ball in there, and they're perfect mirrors, and it's just going back and forth. Well, all we're really saying is that this is E equals 5, okay? Well, if all I have to do is bring the two things really close to each other, okay? I mean, just annihilate that distance thing. So I make them a 1,000 times closer, or 10,000 times closer, 10,000 times closer, and now I have 50,000, okay, energy units, right? So all I had to do was bring these two things 5,000 times closer, 10,000 times closer, and I've now changed from 5 to 50,000. So this is where the c squared comes in. C squared up here. This is where it comes in, is that all you're really saying is c squared is telling you you've taken electrons that are at 0, which would be, okay, they're really far apart. They're a meter apart. So at a meter apart, it's something less than 0, right? Their energy is 0.00001, let's say, or some kind of stupid notion. That's how much energy there is between the electrons. Measurable energy. And then it goes to this c squared thing, amount, this preposterous amount of energy. Because, I took it from a meter, and I brought it all the way down to where the two electrons are, 0.0000000000000000000000005 meters apart. So I multiplied their distance. I changed their distance a billion times, or trillion times less distance between them. An apple is to an atom as the Earth is to an apple. I mean, I've made them really close to each other. So I didn't make more force bits, right? No, I didn't make more force bits. All I did is force force bits to be trapped between things that shouldn't be this close together. So it's the fact that you've brought the electrons so close together that's created the illusion. It's created the same thing as this, right? So to create that much energy here, so if I wanted to have the same energy between the ping pong paddles at 1 meter, I would have to put a billion little arrows in here, a billion ping pong balls. There'd have to be a billion ping pong balls for this to equal this, right? So that's the way to understand it, really, is that you're not making energy in the form of the force. You're making energy in the form of the fact that you've put two ping pong paddles way too close to each other, and the paddles are going to move out. And when the paddles move out, they're going to act like a force. It's going to act like they're full of arrows. And in a sense, they're going to be full of arrows because they're going to absorb everything in the available atmosphere to move. That is, there's going to be stuff jumping in their boats in an insane rate as they move away from each other. They're going to collect everything in the go away direction. So every bit of force, every bit of gravity, every bit of everything will be absorbed by them as they shoot away from each other. And that's the nuclear bomb chain reaction, blah, blah, blah. As they start absorbing all the force, they're creating an insane shadow on every atom. And every atom falls apart because it's not in a neutral force anymore. It's not in the real universe anymore. It's in this completely black universe where everything just disappeared. All the stuff pushing on one side of it. It's like if I evacuated the atmosphere from this side of me, I'm lost, 15 pounds of pressure on this side. And I'm going to be pushed into that vacuum at an insane rate because you just evacuate. It's like people squishing through the airplane window, at high altitude. The pressure it's an insane change in the pressure environment for everything around the atom that goes nuclear. So everything around this atom, that all of a sudden these two electrons flew away from each other, these electrons to fly away from each other are absorbing every bit of energy going in one direction. None of that energy gets to anything else. There's a huge void. Everything starts jerking. And as everything else starts moving this way, then they're absorbing all the energy going that way for everything on this side. And everything on this side saying all the energy's gone, all the pressure's gone, and they start moving. So everything's getting insanely jerked by this absence of atmosphere. This all of a sudden bubbles of vacuum just move into somebody and they just get smushed right into it. All right, that's a good explanation. So thank you for asking the question, because that's an important point that I'm sort of mushing sometimes when I talk about trapping more force. You don't need to trap more force. All you need to do is create less distance between. As soon as you create less distance between electrons, you're creating more force. There just has to be one ping pong ball between them. And all I have to do is bring them closer together, and I'm creating, in a sense, the obligation for the electrons to absorb a lot of force. And I actually had to push them together with energy. I had to push them close together with a whole lot of force to get them that close. So they've already yinned, and they're inevitably going to yang. Not inevitably, but I mean clearly you can make them yang. You've yinned them, you've put a bunch of energy in to get them close. That energy didn't stay in, but it's in the form of them being that close. So the energy you used to get them close, you gave back, okay, in a sense, and that's the magic of an atom. But the energy to go back out, they will absorb to expand. So they're going to absorb a tremendous amount of energy to expand away from each other. And it's that absorption that breaks the system. It sucks all the. It's like somebody pulling all the electricity out of the grid, and then all of a sudden the lights go out in New York, but something else took all the energy, and that's what's really happening. All right. Okay. Electron relative to the atom's radius. All right. So how wild is the jiggling? Okay, we did that. What is your suggestion the distance between protons and electrons responsible for again? Okay, so the distance is critical, okay, to the idea of taking a single bit of energy and making it very powerful, potentially very powerful. All right. What was... Okay, we did that. What was your suggestion? What was it you suggested the distance between protons and electrons to be responsible for again? Okay, so it's responsible for confining energy, and when you confine energy, you multiply its potential. Something like that. Electric potential or conductivity. So I don't know exactly how that goes to conductivity at all. So I'll just pretend I didn't read that because I don't know what that means. When looking into data from the particle colliders, did you see anything about the discovered particles and their sizes? Well, there's something, just innate in what they're saying. So if they say there's 3 quarks inside of a proton, obviously quarks have to be smaller than the proton, right? Makes sense, sort of, but I just don't think there's any practical way to distinguish in these subatomic particles a difference between their mass, their size, their density, their volume, however you want to. It's just not easy to measure any one of those things without making assumptions about something else. So without your assumptions, you really can't do any of that kind of deducing. And I'd say the real argument is just deducing proximity and relative proximity, and sort of this whole ping pong paddle argument that there is kind of an infinite end to the multiplication. And you could argue that if the as I'm arguing, there's all these little subtle tricks to it. I'm sort of arguing that from a distance it's going to look different depending on how it's moving, and when two things move into each other there's a consequence. So I'm sort of arguing that there's no way to get too close to something else, because the idea is that everything's sort of shooting energy in maybe like this in some sort of normal condition. So there's a dead spot actually, between the straight line path. Okay, so if it's moving towards, so if you are moving into something, all of a sudden now you're making more energy here. Okay, and if you're you're not moving, then the energy's spread out, let's say, evenly in all these directions. And then if you're moving in the opposite direction, okay, then you're making less energy here, which is creating a reason for you to go back. So it's not as simple as some sort of. So there are positions you could argue, because they're spraying, their reflectivity turns on and off with their motion. There's a real practical point where you could reach where it stops. You just can't get any closer or further away, because you can't create anything between you, because everything misses. So the reflections, the mirrors are imperfect enough that when the ping pong ball is bouncing back and forth, as you get closer and closer, there's a little curve to it, or there's something, and that curve becomes impossible for there to be these reflections. So there's no more ability to push apart, and there's no ability to get any closer. That's the wrong analogy. I'm using the repulsive argument when I really should be using the red and green argument. So for the red and green things, there's a real tendency to be attracted from a distance, in this area. But you go too far away and you go too close, and the system breaks down, because it's not, the laser beam doesn't shoot perfectly straight. Something like that. All right. So what they see in particle colliders, again, the argument is that they're not really seeing stuff that has any durability. So just understand, they're saying, look, what I'm arguing is that the electron and the proton are really elemental things. They're nothing to them, really. They're just holders of momentum. So the argument is that the electron is just trap stuff going in circles, little birds you've put in a cage, and the birds have a direction. They want to fly away in a direction, but they can't because you've trapped them. But they still have that direction. They still have the way they came in. They still want to go that way they came in, even though they're trapped in this big cage. So they're going to fly out in the direction they were going when you put them in the cage. That's their will. So we're basically saying, look, an atom smasher saying, look, I'm going to bust a proton. Well, it's like saying, okay, here's the boat with the rowers in it. Let's say if I break it here, more rowers are going this way. And if I break, on this side, there's more rowers going this way. So the two pieces go this way and one goes this way. And if I break it into 3 pieces, well then, this one's going that way and this one's going that, and you could even imagine that they might even go away spinning. You could even imagine that's possible. And so they will call these things particles, but they're not really particles. They don't last, they don't survive, because now they've lost their pattern. They've lost the boat, so the water gets in, they sink. But before they sink, they might do something interesting. But it's not really a particle, right? It's a part. It's a fender. It's not the car. So they're basically saying, look, proton's made out of cars, and I'm arguing, no, it's made out of wheels and bumpers, and you can break that shit off, and it sort of looks different. A wheel looks different when it's flying out of the wreck than the bumper looks, but same difference. It's just parts. So let's understand, none of the stuff they've ever discovered in a particle accelerator or an atom smasher, none of it lives. Okay, it all dies. So everything besides an electron and proton has no durability. It doesn't last 1 second. Okay, it just doesn't. It's just dead. So the whole conversation is a little bit silly to say that's the same stuff as the stuff that lasts 10,000 years or 10 million years. It's not really the same stuff, right? So I want to say anything else about that? I don't think so. Yeah, I did. So again, see, we go one layer deeper and say, okay, let's get rid of the boat, and we're just saying we have a pattern. So let's say an electron is, in its foundation, it's a pattern, and the pattern is, 1 million deep. Okay, so there's a million little bits of force, all stuck to each other, but there's an equal amount in all directions. So in a sense, it has a hard little core, and that's the pattern. And then what you're really talking about is how much of this surface can I change? So in a sense, all you were really doing is affecting the surface. So we can affect 3 or 4 or 5 deep. So out of a million, the 5 deep we can screw with, where we can take 5 going this way, 5 in that direction, and we could shave those off and put them over here. All right. And so the durability of the electron is the fact that it has a core that's neutral, and that it's really just this surface layer that we're changing the pattern of. But the fact is, it only can hold so much of this atmosphere. So it's like the atmosphere on the Earth. You can't, you can like move the tides. You can move the water. You make the water a little thicker on one side because of gravity, and a little thinner on the other side. So you have these high and low tides, being caused by this pressure actually off the top of the, off the poles is where it's really going. It's pushing water off of the poles. But anyway, it doesn't matter. The fact is, I can make it a little thicker on one side and a little thinner on the other side. And then you could argue that that's sort of what's happening to the electron. It's gaining a little on one side, losing a little, and that's the pattern you're changing. So that's the changeable part of the electron. And it'll decide which way it goes. Now, the point is that it goes as if this stuff doesn't weigh much. Because it can't really be a million of these, and then you change 6, and you make it go in a direction. That's really not going to work. So obviously the stuff in the core has to somehow be neutralized. And I would say it's neutralized because it's not being affected by the drag thing, right? There's no force can get to the interior. So that's what I mean by the durability of the pattern. Nothing can get to the interior. All you can do is poke holes in the exterior. So in a sense, there's no drag for all of this stuff. So in a sense, it has no mass because it has no drag. It can't interact with the field. And the only thing you're going to interact with is the atmosphere of the electron. So anyway, but it's going a level deeper that I don't, for the sake of making an argument that conventional physics is full of crap, I don't really need to go that deep to explain the electron. Linking into data from particle, okay, we did that. It would be very suspicious if they were all the same size. Well, I think it's very suspicious to think of them as the same kind of thing. To think that quarks are somehow just as real as electrons and protons. I think would be stretching reasonableness. All right, maybe take a break. Maybe it's enough of a video. It's a lot of stuff, but we'll probably do another comment. And I was going to do a little Ken Wheeler, but I don't think that's going to happen. Anyway, I'll be back shortly, I think. I'll be back, I think. So this other comment is sort of related. Happens to be to what I was just talking about in a way. So anyway, let's go. Yeah, clickbait titles are generally annoying. I remember when articles claimed Stephen Hawking said black holes do not exist, when in reality he was talking about how the event horizon might work differently than we currently assume in terms of destructive nature, theoretical firewalls. Well, I don't even know what this firewall word is, just kind of bullshit. But anyway, I don't know how you build that into a black hole, but whatever. But it is an interesting... See, I think they ought to just stick with rational language, like neutron star sort of makes sense. And then you could say neutered matter or some other kind of term to get to this point that there's this, as I was just pointing out, okay, so you have these two things and you have a ping pong ball between them, and the idea is as long as that ping pong ball's there, there's this potential pressure. I mean, it's a huge amount of pressure, actually, right? I mean, there's a lot of pressure if they're really, really close together. But what if I could take these two things, two electrons, and I could take the ping pong ball out, theoretically? Well, then they're kind of neutered, right? I mean, there's nothing. There's nothing happening here. It's just sort of nothing, right? I mean, they can have this external pressure pushing them together, and they'll be shielding each other and whatever, but they'll just kind of sit there next to each other and be kind of harmless. As long as something can't get between them, they can't know they're right next to each other. So if I have two ping pong pads, no ping pong ball, there's no reactivity. There's nothing. There's just they're dead paddles. They're just dead. So in a sense, you could theorize that, well, maybe you can do this with matter. And a neutron's kind of an example of the first step, in the sense that the neutron is, I would say, reasonably suspected that it is a proton and an electron really close to each other, okay? Like the electron's riding right on the proton. I mean, I have the colors inverted, but whatever, it doesn't really matter. So the idea of stacking neutrons, you could say, okay, I can create a system that doesn't have any ping pong balls in it, So there's just no potential for this thing to do this aggressive moving in a direction, and so you could say you could get a lot of mass. Everything has mass here. You get a lot of mass in a small space, and so this gets to the size of atoms again. So you can make you could have this argument that the regular atom is this size, and that the neutron atom is a much tinier thing, in some sort of neutron star. And so you've consolidated matter. But black holes are a whole nother thing, where they're basically saying the matter doesn't exist anymore. It doesn't take up any space. And that's where they go way too far, in my opinion. They're just making this, and they're saying in a sense that the external pressure is endless. Like there's an inexhaustible supply of more pressure. So black holes are based on a theory where there's no bottom to the well. And I would argue there is a bottom. There's only so much pressure from the external universe that can be made, and so there's an end to how close you can get this stuff, because there's an end to how much you can rearrange it. But I'm saying that there's theory to say that yes, if you could compact a bunch of neutrons in a very small space, but again, that's all based on their understanding of how big the space of the electron orbits are, and by comparison how small the neutrons are. So it just kind of depends on whether any of that theory is right, how big a difference it makes in terms of how much empty space there is in the matter. So all you're really saying in a black hole scenario is that you're evacuating the empty space, you're evacuating distance and making the thing more dense. But I don't see how that means a whole lot in the sense of the size of the universe and all this. What's the difference? What would the difference be if the sun our sun was the size of a grapefruit or it's the size of the sun. It really doesn't make any difference, right? If you had the same little thing inside the sun, I mean, if you just took the sun's corona and just compressed the sun, but it was creating exactly the same amount of photons, it makes absolutely no difference. All right. I mean, it's going to be as if the sun was really there, right? I mean, from our perspective, the amount of energy is going to have to stay the same, so it's going to appear almost exactly the same. The corona will now look huge, and the sun will be small, but the corona is going to be so big, and it's just not going to make any difference. I mean, from our perspective, it's going to look almost the same. And it's certainly going to be the same energy, so it's not going to matter. Same gravity, same everything. So why people fascinate over, shrinking matter? I just don't get it. Anyway, definitely not your job to debunk all that, although I do think it is a kind of telling how certain modern theories depend on additional variables or additional theories to not completely destroy the existing paradigm. Well, they have to concede something's broken, and they don't want to do that, so they fix it by breaking it. I think cosmological constant that once was removed from physics theory as Einstein's blunder, only to be reintroduced later to explain away another problem. And I don't even exactly know. There's a catch to that whole cosmological constant in the sense that, you're talking about Einstein's theory, so you're just this relativity stuff, and you're saying, well, how does relativity oblige you to create an expanding universe? And I don't even know if I can draw any of that to make any sense, but I mean, it all has to do with this idea that I would argue that your mathematics is always going to get corrupted by the sense that you have to create the initial condition. And do you put the energy in the initial condition, or again, do you have the energy coming from the outside? And so depending on which way, if you put the energy in the initial condition, it has to go out. But if you put it on the outside, then you're going to have some opposite defect where everything's going to get ultimately compressed. So I'm just saying that depending on how you start, you'll have to account for the energy going the opposite way somewhere. So it's a yin-yang system. Which one do you draw first, the yang or the yin? And depending on which one you draw first, you're going to have a universe that collapses into nothing or a universe that expands too fast. So I think that was the invention of the cosmological constant, was basically to say, if you start with a yin, you automatically got a yang, and if you start with a yang, you automatically got a yin. So it was a way of balancing for the fact that you have to start somewhere. And so I think that was the flaw of the cosmological constant, it's necessary, no matter how you picture the initial condition, you're going to be stuck with having to have some way to balance against that force, because it appears to be steady state now. So you have to fix that. Is it collapsing or is it expanding? It has to be doing one or the other if you're going to create a starting point where you put something in. But you're not starting with balance. You're starting with imbalance. So you're either creating something exploding or something contracting. And I think that's all that was about. And so then they invented this notion that somehow all the objects are moving away from each other, not because they have any real velocity. No, there's this fake notion that somehow the distance is growing. Somehow a bunch of empty space is being created between them. And so they're not really moving away from each other. They have no velocity, but just a bunch of space is popping in there. And that the space is actually popping in between the photons, moving between them. So the photons are getting redshifted as they travel. Not because something was moving, not because the train was going by you was moving. Do you hear the sound change? No, you're hearing the sound change, but somehow the universe is compressing or expanding. That's just... Frankly, that's just idiotic, as an explanation. And again, this just has to do with this stupid redshift thing, because the distance between the photons appears to change with the length of time the photons travel through space. That is, the faraway objects the photons seem to have a drag factor where they've spread out a little bit. They should be here, and they drag with distance. that we're going to assume the universe is expanding when there might be other explanations for why photons over distance lag a little. Battery's going low. It's not enough sun lately. Keep my solar panels aren't doing their job. Oh, well, I'm gonna turn this thing on too. Turn that off. And we'll see if it turns back on again. That's not gonna help it any. Anyway, so now that I'm sitting up now, it's strange. I must have hit the camera, right? I must have done something. Anyway, need a little break. Okay, so he didn't say anything close. Anyway, definitely not the job debunk. Okay, did all that. Cosmological. Explain another problem. And then they added dark energy as what should explain away the inaccuracies of there being a cosmological constant. Except, unfortunately, dark energy was never detected to exist as a new force. Well, yeah, it can't really exist as a force because it's actually creating the white space somehow. I mean, it's, it's such a bold explanation, and it's based on just nothing as evidence. Again, all you have is a phenomenon of redshift. That's all they're basing it on. There's just no other evidence of this expansion except for that phenomenon. And it just seems such a stretch to say you know enough about photons to say that's why the photons change their frequency is because their frequency is because a bunch of empty space is being created. When we have no way of detecting that in anything else, I mean, it would be sort of critically important to the whole function of atoms. If you're saying that now there's a bunch of empty space being created in atoms, that means you're moving all the little bits apart, and that would have I would think, a rather catastrophic effect. I mean, the minor effect it has on the photons over time, you can see that it's kind of, but it's still kind of a dramatic change in the distance between the photons. You're talking about hundreds of nanometers in distance, and yet you can somehow change the photons by hundreds of nanometers. If I change the insides of the atom's nucleus by hundreds of nanometers, the atom's going to fall apart. So how do atoms last 10,000 years if they, or millions of years if you're breaking all apart all the time? So it doesn't make any sense, frankly. It seems sometimes sticking with an existing paradigm is deemed more valuable than questioning existing theory when something turns out not to add up. Yeah, well, this is the biggest. I mean, I'm finding it a difficulty also. I mean, there's times when I say, well, maybe it's time to try to mix this up and see if I can find a better angle, because this angle is a little dead. It's not going anywhere. The triangle isn't working, and so you say, well, let's try a square. Let's try something else. But the balance between that, where you're deciding to change the foundation, can be a mistake also, because you're on the right track. You just haven't gotten the right track working right. But it's you're on the right road, and changing the road, is just going to be a dead end, and so you're just kind of wasting your time, and you don't want to do that. So some of that is understandable, and not resisting changing what's sort of working and sort of seems like the right road. But I guess my fundamental argument to people is, I don't know how any of you see this as looking like the right road. To me, photons waving and doing all this hyperboloiding and all this crap that people are making up, how does that look like the right road to you? To me, that just overtly looks like a wrong road. That looks complicated, messy, sloppy, stupid, silly. It's like giving the photons ESP. I'm seeing it as being almost perfectly analogous. I think there's almost a perfect analogy in the sense of creating entanglement and creating all these phenomenon that don't make any sense, that seem way too complex for the simplest elements in the universe. Again, the argument is you can't find these unicorns and dragons anywhere in the big universe isn't doing it, right? I mean, the constellations barely even look like a bull or a horse. Barely. Okay? I mean, there's just no evidence of any of this wooey shit in the big, huge universe. The one we are existing in is just dead quiet when it comes to unicorns. And yet they're just saying they all exist here in this little tiny place that we can't see. They're all in the shadow. You know, and isn't that convenient that they always seem to be able to hide from us, these little gremlins? It just sounds like gremlins. You know, it doesn't sound like this is Right Road at all. To create all these magical properties in the simplest things, the smallest things, have all the magical properties. It's just giving the brain to the DNA molecule. It's almost that stupid. Oh no, our brain is in the DNA molecule. You know. No, DNA molecules make brains. It's the other way around. So anyway. So, till the next time and such. I think I adequately performed my task. Last couple of videos pretty solid. So, till the next time and such. Yeah, that's enough. Thanks for the well-wishing and such regarding the whatever, the event, anyway, and such, and so forth and whatnot. Till next time.